Welcome. Everybody excited about layer 2 networking? Thank you, Kyle. Okay. I have no better title for this, so we'll just ignore the title slide. There was a tech talk on layer 1 networks some number of weeks ago. The recording for that got botched, so I'm going to be working on doing a better version of that and uploading it to the one wiki page for the Racksburg Tech Talks soon. Just as a refresher, these are the OSI layers that we're going through. We're talking now about the second layer called the data link layer. In layer 1, we're talking about wires and cables and electricity and how bits are actually moving along those connections. At layer 2, we're talking about frames. So I might slip up and say packet or something like that, but that's wrong. We're just talking about frames at this layer. Oh yeah, those are those cables. Pretty. At the data link layer here, the purpose of it is to control the use of that physical medium. There's very little logic, but there is some logic here. So like, unlike at layer 1 where it's just dumb and energy moving through a medium, at layer 2 there is actually logic being implemented by devices. There is protocols being used, stuff like that. It is commonly divided up into two sublayers, the logical link control and media access control. The layer 2 protocol that most people know about, layer or Ethernet, doesn't actually implement much of LLC or logical link control. That's typically only seen in large scale, low reliability networks such as WANs and satellite communications and cellular networks and stuff like that. What you will see in various Ethernet related standards like 802.blah, you'll see things like CSMACD, which is collision sensing media awareness collision detection or something like that. Collision sensing multi-access. Thank you, Alex. So that is, in a nutshell, it's just when you have a shared medium, when your layer 1 medium is something that multiple nodes and devices can be talking on at the same time, you have to have some protocol which makes sure that they don't talk on top of each other or that one node's signal does not override another. So you'll see that in older networks with hubs. You'll see that in fiber optic networks where you only have a single channel of fiber. You'll see it in coaxial based networks because there's effectively only one transmission medium there, that one coaxial line. And you'll also see it in a lot of wireless networks because of course that one wireless frequency you're broadcasting on is a single medium. There's multiple sub-frequencies it may be able to pick from, but there's still collisions and you have to say that this access point is allowed to talk and now this node is allowed to talk and now this access point on a completely different network but also in range is now allowed to talk and they all have to share that spectrum. So you have all sorts of different algorithms that all start at layer 2 to define who can talk when and how and where. Something else that layer 2 is known for is collision domains. So at each step up in the network now, we're going to be talking about different types of domains. So at layer 2, we call it a collision domain because you have the possibility for these nodes to collide with each other. If your experience with networking and computers is old enough, you'll remember hubs, and you'll remember that you have a link light on your hub, you'll have a data light on your hub, and you also have a collision light when two packets enter the hub and only one leaves, because they were both trying to talk at the same time, and one of them got in the way, and it died. And there was a protocol at the time that, well, it's still technically part of the protocol, but nobody uses it, where when it senses that, the hub will send out another, like a stop or a back off signal to all of its nodes saying, whoop, there was a collision, everybody stop, and then everybody starts backing off some amount of time so that they don't start talking on top of each other again. You won't see this anymore, and actually it's much to the dismay of networking labs at colleges, like where I went to college, because everybody at colleges wants to use hubs to sniff traffic on ports and stuff like that and investigate protocols. So another archiving come up with weirder, different ways to do that. at the next OSI Tech Talk on Layer 3, we'll talk about broadcast domains. So at every layer now throughout this network topology, we'll also be talking about a different type of addressing. So at layer 2, we have MAC addresses. People here in Rackspace email may have heard me asking for MAC addresses earlier today, which we'll get to that in a minute. The MAC address, though, is, in essence, it's tied to your hardware. That address is supposed to be for that physical device that you have that is connected to some network somehow. Typically, your physical device is only capable of one type of layer 1 communication, so there's a one-to-one connection there between the layer 1 technology you're using and the MAC address of that device. There's also, just like all other addressing, there's reserved addresses for this and that. There's a broadcast address when you want to talk to multiple nodes from your one location, stuff like that. The MAC addresses that this is getting more and more specific about Ethernet because who cares about any other layer 2 technology. But the MAC addresses that you are familiar with are split up into two parts. There's the first 3 bytes, which is the vendor ID, or the OUI, organizationally unique identifier, I think. And then the second half of it is unique to your one device from that vendor. So let's say Intel makes a network card, and Intel will spit out thousands and thousands of network cards that all have the same OUI programmed onto them, and then they'll just keep incrementing the serial number on each of them, so until they exhaust their entire OUI there, because whatever 8 to the 3rd power is, or no, 256 to the 3rd power number of addresses for that one OUI. So there's, whenever you start assigning things to organizations, there's a standards organization to keep track of it. So that's what IANA or ICANN, I always get those two confused. That's what one of them does. And so here's a cross-section of a few random OUIs. You can go to, oh, it's the IETF, that's right. IETF.org has a text file that you can download, which is all of the assigned OUIs as of the time that you download it. And so here's a few random ones. You'll see Hewlett-Packard, LG, Nintendo, Intel, Sagecom, whoever the heck they are, HTC Communicate Corporation, HiUI Technologies, whatever they are. Yes. If you are a large organization and you manufacture a lot of devices, it is quite possible you're going to exceed the however many tens of thousands of devices within a single 3-byte OUI that it allows you to generate. Because you only have these 3 bytes to create unique devices from. 16 million from our resident computer science genius. So large organizations, certainly Intel, Dell, Nintendo, HTC, I'm sure, they have multiple OUIs registered for the large number of devices that they manufacture and have to stamp with a unique number each time. Even Rackspace, for whatever reason, has an OUI. This was a surprise to me. We only had the one, but I grepped for Rackspace just on a whim in that text file when I was building this presentation, and I found us. That's our OUI. I have no idea what it's used for. Maybe somebody at Castle that is connected to more teams than we are here in Blacksburg will know and can send me an email and tell me why. I have no idea what the difference between hex and base 16 in this context is. Yes, virtual machines at Rackspace do have MAC addresses. If you look up the OUI of those VMs, it comes from Xen, not from Rackspace. And I'm sure we have, this is Rackspace's only OUI, and I'm sure we have more than 16 million possibilities or VMs or whatever out there. So, I don't know, maybe it has something to do with Open Compute Project, I don't know. Maybe. I'm sure I'll find out soon enough. So if you want to look up, without downloading that text file and grepping through it, who owns an OUI, I always just do a Google search for OUI lookup, and the very first hit there is the Wireshark webpage of the OUI lookup tool that they host, which is a very nice little tool where you can type in however many MAC addresses you want, and it is really clever about formatting and parsing, so you can just dump in whatever you want there, and it will pick out the numbers, and it will show you, here are the people who own these OUIs. So these are a few MAC addresses of various people around Rackspace email. Neat, huh? And this is also really helpful for network sleuthing when you don't actually have access to anything, but you see a bunch of MAC addresses in your ARP table, or you see your switches saying that these MAC addresses have been sensed on this port or whatever. And so you can look up the OUIs for all those MAC addresses and say, oh, this is a Cisco device, so that's probably another router. Or this is a Dell device, so that must be a server sitting in my edge network VLAN. Why is that? Stuff like that. Real fun stuff. Another use for it is in playing around on what is happening in your home network. So if you're a geek like me, on your phone, you have some app like this that allows you to send out broadcast packets throughout your network and see what devices come back and put it all together in a nice little interface like this and correlate host names with IP addresses and stuff like that. And so you'll see on my 2 different wireless networks here, it's all the same layer 2 domain, but I have just 2 different SSIDs for 2 different frequencies. And these are the various devices on my network at the time that I ran this search, however many months ago this was taken from. And so you can see it's taking the MAC address of my Mac Mini and saying that it's an Apple, and here's hypervisor I run, which is an Intel NIC, and that's a Cisco Linksys WRT54 access point, etc. Yeah. Was there anything else on there I wanted to point out? Yeah, my wife uses a laptop that has an Intel NIC, yep. My router uses a external USB D-Link dongle for its internal interface, and then I have a D-Link access point. Samsung, oh yeah, my television, I have a smart TV that plugs into the network too, so that's Samsung's OUI there. Down at the bottom, some Android device I have on the network apparently, because it has an Android host name made by, with a NIC at least, made by Murata Manufacturing. Oh, and then that's my Kindle. Yeah. Oh yeah, that's the other thing, XenSource. So mirror.aregner.net is a VM on that aforementioned hypervisor. So Xen makes MAC addresses from their own OUI. So that's my hypervisor's MAC. This is the VM's MAC. Oh, and ADR Lumberjack, that's also a VM. It runs Logstash. Thank you. I like that too. So, along with protocols and standards, there is a header. So, at each new layer of the network that we were going to be talking about in this series, there will be a new header to talk about, and this is the Ethernet header. This is also going to be the simplest of all the headers. It has destination and source address, which is your 6-byte MAC addresses. It has 2 bytes of a field called ether type. Then you've got your payload of whatever sort of data it is that you're shuttling around, and then it has a CRC checksum at the end, 32-bit checksum. And if we take that ether type, this is something else defined by a standards organization that says that 0x0800 is IPv4, and 86DD is IPv6, and IPX is 8137 for people out there who love IPX like I do, etc. So this is just a few sample protocols out there that you can use the Ethernet header for. There's lots and lots of them. When we talk about VLANs, remember this one, 8100 for VLAN tagged frames. So VLANs, it's a virtual network, a virtual LAN. So I guess I should back up a moment and say that a LAN in this definition is your local area network. It's your local, everything that is connected to a switch or hub or whatever up until you get to a router. because a router bridges networks, and that's not this talk. So everything in your house is probably a single LAN. Everything within one part of this office is probably a LAN. Everything within one of our Rackspace email environments is a LAN, well, for one team at least. So you can split these up virtually and not have to worry about plugging in all the things that you want on the same LAN into the same switch. So you can say, this is a very simplified diagram, but your switch port can say this port is on VLAN 12, this port is on VLAN 10, and if you were to send a broadcast packet or whatever out this node, it would only be these 4 that see it on VLAN 10. Even though VLAN 13 is plugged into the same switch, it wouldn't see it because the switch knows that that's a different network. If you want to bridge between those networks, then you need a router. You can also have trunk connections, which is essentially just a port or a logical or physical connection which has been configured to be smart enough to know the difference between different VLANs. Because a random Ethernet frame that comes out of a node plugged into VLAN 13, the switch is just going to assume that's VLAN 13 and not respect anything else in the packet as far as what network it's on. So that's done by co-opting that ether type header that we saw a moment ago. And instead of, you'll see that what was just the 2-byte type ether type field becomes an 802.1q tag. So if you ever see .1q somewhere in a Cisco config, that's VLAN tagging because that's the standard that defines all of this. You'll see that 8100 down here. So after it's done reading the source MAC address, it'll see 8100 as the ether type, and it will know that that is a VLAN tag frame. So it knows that it needs to keep reading a little bit more and find out the VLAN ID. And you've got 12 bits for a VLAN ID, and if you take 2 to the 12th, that's 4096, which is exactly how many VLANs you can have in your zone. So people out in Rackspace NetSec, that's why your AGX net zones are 4K, because that's as big as Ethernet will allow us to make them. Then after the .1q tag, then you can have your type length. So there's like 2 type headers in a tagged frame. So you've got the 8100, which says this is VLAN tagged, and you've got IPv4, v6, ARP, whatever after that. If you have a switch like back here that has to take a frame from a node on VLAN 13, for example, and it goes into the switch and then over a trunk to somewhere else, it has to take that untagged frame from the node and then apply this tag to it and then ship it off somewhere else. That means that the CRC is going to change, which means that anytime you do tagging on a switch, it has to recompute that CRC. So that's why it's changing from an untagged to a tagged frame. The CRC would also be changed. It's not just the CRC of the payload. Fortunately, there is a lot of really fast hardware that does this for us. Cisco is like, they invented this business decades ago, where you can create special programmable microchips or ASICs that come from the factory already wired to do Ethernet switching and VLAN tagging and recomputing of CRCs for you. So, you know, we sometimes as we're building our networks and we say, oh, it's going to be this many packets per second or this many bits per second or whatever, and can the CPU on this router handle that and stuff like that? Well, we're not at a level yet where we need to worry about the CPU, because in high-end networking equipment at least, all this sort of stuff is done in hardware, and the only limitation to how fast you can push Ethernet frames back and forth and recompute VLAN tags and CRC checks and stuff like that at the end of your frame is only limited by the speed of light that you can push electricity through these chips. Like at the higher end Cisco switches, like the Nexus 7K, for example, it has, you know, you can have a 13 slot chassis, and each one of those slots can have 48 10 gigabit ports, and you know, you can go in there and configure it to do whatever you want. So, but ultimately, the operating system on that Nexus 7K is smart enough to say that these ports can possibly be in these VLANs, and so when you get a frame in on this port, run it through this ASIC, check it against this CAM table, which is a cached address, I don't know what CAM stands for, something like that, which is a MAC address table of these are the MACs that I've seen before on these ports. So it can run that through a hardware buffer and know exactly what it needs to do with that frame as fast as that electricity can move through the chassis. That means that the limitation on your switching fabric or whatever is more so about layer 1 and about what you're doing after you've switched that frame, or maybe you're applying ACLs to it, or maybe you're doing something that they don't have an ASIC for yet. Is there a question?
Yeah, that seems like a massively parallel kind of problem. Do they have these, I guess, CPUs designed for that? Because like if you're getting packets in on all these different ports, right? Why run it through one processor rather than a ton of really tiny single ones, or maybe just design it like a GPU where you can handle like a ton of parallel operations all together?
Yeah. So the question was that, or I guess the statement was that it seems like a very parallel question. Why would you have to run stuff like that through a single CPU? And I'm not up to date on the latest internal Cisco architectures of some of the higher end stuff that they have, but because it's been 5 years since I worked at Cisco. So the reason is that, actually, I know that some of their devices do have multiple CPUs for different purposes. For some, like if you look at the ASA, for example, the ASA, especially the newer ones, do have multi-core CPUs, but it's more so like a software design choice / flaw in the way that they make them, that you can only run this one operation on one CPU because that's the way they implement it, because they thought that, oh, nobody will ever need to do more than this many per second on this one feature or whatever. But at this level, at layer 2, there's very little that you need to do that you don't have an ASIC for in a high-end switch.
I was under the impression that ASICs were very focused in terms of their design. They're not CPUs per se.
Right. Yeah.
They're they're logical controllers. So
Sure.
there is a CPU in there that runs an operating system, but some of the chips that handle injecting the VLAN ID and recomputing the CRC, things like that, that's handled by specialized chips. That
Right. But I think he's saying so that you could theoretically have multiple of those ASICs.
Oh, absolutely. Yeah, because they have other ASICs for VoIP and all kinds of other very specialized encryption and everything.
I guess the reason why is because they're so cheap, so you only need one.
Yeah. So for the remote people, assuming they can still hear me, is the discussion here is that the ASICs are only meant for these very common low-level functions like recomputing CRC checks, looking up a MAC address in a CAM table to figure out what port it needs to go back out on and stuff like that. So actually, my larger picture here is of the motherboard of a Cisco VoIP phone. You've got an Ethernet controller here. You've got a boot chip, whatever that means. You've got a couple of ASICs here built by Texas Instruments, and then you've got some RAM, and I'm sure there's a CPU on here somewhere. The CPU is responsible for, like, I guess, the most number of things, but the most things that the thing needs to do, as in looking at every single packet that comes in over the wire and make sure it's for this device. Like, that's something that it has to do really, really fast, because if you have a lot of broadcast traffic on your network, you don't want your phone to crash. So that's something that you can do with an ASIC. And that's something that we've been doing since the beginning of networking time, and so I'm sure there's a lot of really common ASICs out there to do it. This is a line card, actually, from, this is probably from a Cisco 7600 router / switch, whatever you want to consider it. And the line card actually has these built onto it. So in this 13-slot chassis where you've got hundreds and hundreds of ports and a main supervisor controller and stuff like that, a lot of times the Ethernet frame doesn't even need to leave that one line card. It can go in the line card, hit an ASIC, and realize that it needs to go back out a different port right next door or something like that. And so it can happen at the speed of light within that same line card without ever having to hit the backplane of the chassis at all. And then this is Cisco's one of their newest, fanciest N-Power X1 ASICs, whatever the heck it does, I don't know. I tried looking up information for it, and I just got a whole bunch of sales pitches. What was that? Yeah, N power, good, right. So talking about enterprise large-scale networks, the last major point I wanted to make here is that as we're thinking about different layers in the OSI model, good networks are also designed with these layers in mind so that you can simplify your design of your network and the management and the efficiency of it by using these layers to guide that design. So this is a basic diagram I threw together of servers in a cab with a cab switch plugged into an aggregation switch plugged into a core router. So in a lot of typical network designs, you'll have a layer 2 and layer 3 boundary where everything below this line is configured with layer 2 logic with like VLANs and trunk ports and stuff like that. And then everything above that is configured with layer 3 logic like IP addresses and static routes and routing protocols and stuff like that, which we'll get to in our next talk. So that means that if you've got a VLAN for, let's say, mail gateways, and those gateways are spread across all the cabs here, so you've got different ports plugged into these different VLANs. And if they need to talk to each other, then it's just ARPing and sending out Ethernet frames that hit the agger and go back down and not have to go anywhere else. If you have to talk to, let's say, a database server in a different VLAN, then it will talk to its gateway, which exists above that line on the router and comes back down through a trunk. It is a lot easier to scale and design networks this way. It's a lot easier to conceptualize them, a lot easier to design them. It also means that if you make one change to a routing protocol here, it doesn't need to screw up and affect things all across your entire topology. So this is a very typical sort of paradigm in the enterprise networking world. And we mostly do it this way, kind of. And I think that's all I got. Any questions? Network engineers who don't know what they're doing. I'm sure there are all sorts of use cases where they may think it's easier to design things maybe what they think is simpler to maybe you want all of your routes to exist on a single core router instead of a multitude of aggregation switches, something like that. I guess maybe if you are designing a smaller network and you aren't worrying about scaling as much, then you might think simpler and not do something like that. Oh, and from Andrew Edwards on video here, TCAM, ternary content addressable memory, is a specialized type of high-speed memory that searches its entire components in a single clock cycle. Really fast stuff, fast networks. Yes? So let's see, do I have? The question was, can I talk about the logic of what happens when a frame comes into a switch, looks at its CAM table, and what does it do after that? So let's say then that let's say that this is a switch, and I've got a server here and a server here, in two different cabs that want to talk to each other. And the switch is the bigger square in the middle here for the people on video. So we'll assume that the server that you are on, the sending node, knows the MAC address of your recipient because you've already ARPed for it or you have already talked to it or something like that. But maybe it's been a while since you've made that communication, or maybe the CAM table's been flushed or whatever on that switch or something like that. So that frame comes out of your source server and hits your switch, and the switch, if it doesn't know where that destination MAC address is already, then its default behavior is to spit it out all ports on that VLAN. And then, no, I'm doing this wrong. And that's how ARP works. Right, because so every single time a packet comes out of a node and into a switch, it's taking note of that source MAC address and putting it into a CAM table, so that next time somebody needs to talk to it, it will know where that MAC address lives. And it's also not necessarily a one-to-one relationship either between MAC address and port number, because the switch doesn't know or care how many MAC addresses or nodes are on a single port. It just knows that this is a list of MAC addresses on this port. So as soon as any traffic comes out of your node, then your node is in that switch's CAM table, all the way up to the top of your topology. So as soon as that source Ethernet frame comes out of your source server and hits your switch, it will know which port that destination one is over here, over there, or whatever. Or if it needs to come back down to the same link, then it will probably not do that, though, because that's like split horizon sort of things, where you route things back to the same place it came from. Any other questions? Anyone on video? No, okay. Well, we have a Cassandra talk on Thursday from the last July, almost a year ago now. I went to a Cassandra training from DataStax and got a lot of really nice in-depth information about how Cassandra works internally and how it cooperates with nodes and how you can manage it and monitor it. So we'll be talking about that. It'll be very Rackspace email focused, but maybe other people will have some interest in it. And then next week, we have the Layer 3 Tech Talk, which is going to be my favorite because I love IP and networks. And prepare to learn about IPv6 again.